Okay, this video is going to be a nice way to summarize all the things that we've talked about in the previous 4 videos. So previously we talked about systems of linear equations and then how you can take that system that you're working with, the system of linear equations, put it into the form of an augmented matrix. And then after you have the augmented matrix, you can row reduce that to reduced echelon form. And then you can take your reduced echelon form matrix and derive a solution from the basic variables and the free variables that you got when you were doing your row reduction. We haven't talked about any concrete applications so far, and I feel like you just have to do that because linear algebra is something that is used in so many different fields, from finance to chemical engineering and pretty much everything in between, in which you can speed up calculations with a computer. So right now we're going to do a practical application. We're going to look at balancing chemical equations, and this is something that you probably first see when you're in high school chemistry, but even if you're going to take college chemistry, this is something that you're going to see again. So just in case you're not familiar with a lot of these terms, I'm going to give some background. A chemical reaction or a chemical equation relates reactants and products encountered in a chemical reaction. For example, we can take the reaction that involves combustion of propane gas, which is C3H8. So the C3 is 3 carbon atoms, and then H8 is referring to 8 hydrogens. And this propane gas is going to combust with oxygen to produce carbon dioxide, CO2, and water, H2O. And then we can write this chemical equation in the form of equation 1 here. So on the left side, we have the reactants, and we're going to put an X variable as the coefficient in the chemical reaction. So X1, C3H8, plus X2, O2. And then on the right side, we have the product. So we have X3, CO2, plus X4, H2O. Okay, looking at the second section of text, we have that when balancing the equation, we're looking for values of the variables x1 to x4 such that the total number of individual atoms on the left matches that of the right. So we have 4 vectors for the 4 chemical species that are reacting with 3 entries, each for the 3 different atoms. So we have carbon, hydrogen, and oxygen. So for these 4 column vectors, we're going to write 3, 8, 0 for C3H8, 0, 0, 2 for O2. For CO2, we're going to write 1, 0, 2, and then H2O, we're going to write 0, 2, 1. And that's going to give us an equation, right, overall. So we have the coefficients plus these vectors for the molecular species, and we're going to have x1, a1 plus x2, a2 equals x3, a3 plus x4, a4. And in this equation, we have that the x variables are going to represent the coefficients in the chemical equation. And we want x variables that when we add up all of the numbers of atoms, so the carbon atoms on the left should equal the carbon atoms on the right, and same for hydrogen and same for oxygen. And that is that we want the reactants and the atoms in the reactants to equal the atoms in the products. And just to drive this point home, we have 4 column vectors, 1 for each molecule. So 1 for propane, 1 for oxygen, 1 for carbon dioxide, and 1 for water. And we want all of these values of atoms of these molecules, the individual atoms of these molecules, to add up and be equal on the left and the right. Okay, and then from equation 3, we can rewrite it so that we have a 0 on the right side. We have x1, a1 plus x2, a2 minus x3, a3 minus x4, a4 is equal to 0. Or we can put it in the form of an augmented matrix, and we have for the first row 3, 0, negative 1, 0, 0. Second row 8, 0, 0, negative 2, 0. Third row 0, 2, negative 2, negative 1, 0. And then we're going to start up with the row reduction. So in the row reduction, remember, we want each leading term of the row to be 1. So we want in the first position, the first entry of row 1, we want a 1. And then in row 2, the second position, we want a 1. And then in the third position of row 3, we want a 1. So we want to put it into echelon form. I've got videos on that, so if you don't know what I'm talking about, you can go back and watch that. But we want our matrix to look like at the end, we want it to look like equation 5. So equation 5 is the matrix with row 1, 1, 0, 0, negative 1 over 4, 0. Row 2, 0, 1, 0, negative 5 over 4, 0. And then row 3, 0, 0, 1, negative 3 over 4, 0. And now the matrix is in reduced echelon form when we've written it this way. And then we can write the basic variables in terms of the free variables with x1 equals 1 over 4, x4. x2 is 5 over 4, x4. x3 is 3 over 4, x4. And then if we let x4 equal to 4, then our chemical reaction from before, remember we have the x variables as the unknown coefficients to balance the equation. We've got C3H8 plus 5O2 to 3CO2 plus 4H2O, and we've balanced our chemical equation. And that wraps up our general procedure for using linear algebra to balance chemical equations. So you can use that with any chemical equation that has a solution. You can balance it this way. And I hope that was a nice first real-world application of linear algebra. In the next video, we're going to be tackling vector spaces and looking at how we can use vector spaces.